In this video, I will demonstrate how you can calculate the gravitational force vector that one object exerts on another one. I need to mention though that this is going to be a quite difficult calculation, so it will be helpful if you review how to calculate the magnitude of a vector and how to calculate unit vectors before you move on and watch this video. Okay, this is the expression that allows us to calculate the gravitational force vector minus, this minus sign is associated with the direction of the vector, the constant g, the two masses, the distance separation between the two objects squared, and the unit vector that points from one object to another. Now, I will show you how to use this expression in an example. We have, so let's say we have a star and the planet. This is the coordinate system. This is the x, this is 0, this is the y, and the z goes out of the page. The star is on the positive x, positive y axis, so the star would be somewhere here. And then I have the planet in a negative x and positive y. So the let's move the origin. The planet would be negative x, positive y, so the planet would be somewhere here. So this is the planet, and this is the star. Now I want to calculate the gravitational force that the star exerts on the planet. So the gravitational force from the star on the planet. Now, I know that since this is an attractive force, I know that the force will point towards the star. So the force from the star on the planet will point towards the star. This is the vector of gravitational force from the star on the planet. And sometimes it is helpful to draw this vector so that you have a feeling for the direction of the force. Okay, now the first step that we need to do these calculations, we have to calculate the vector r from object 1 to object 2. Now in our case it's from the star on the planet, so I have to find the position vector that goes from the star to the planet. Now, to do this calculation, I need to subtract the position of the star from the position of the planet. So it is our planet minus the position of the star. So the second object that you see here from the star on the planet, it's our planet goes first minus the position of the star. Now we have the two position vectors here, and if you plug in the numbers and you do the calculations, you will find that the position from the star on the planet is equal to minus 5 0 times 10 to the 11th meters. Now this vector goes from the star on the planet. So in this picture the vector would be I will draw the vector here so that you can see it a little bit more clearly. This is the position vector r. This is the r from the star on the planet. It goes from the star on the planet. Now the next step in this calculation is to find the magnitude of this vector r. So I have to calculate the magnitude of this vector r from the star on the planet. Since I have the three components of this vector over here from my previous calculation, you can include these numbers in the square root of the x component squared plus the y component squared plus the z component squared. And if you do these calculations, you will find that the magnitude is roughly 7.1 times 10 to the 11th meters per second. It is a good idea to do for practice these calculations just to make sure that you're getting the same results as I did. Now, the next step is to find the unit vector that goes from the star to the planet. And you can find the unit vector if you take these three components, the vector r from the star on the planet, and you divide this vector with this number, the magnitude of the vector from the star on the planet. So this is the magnitude of the r vector from the star on the planet. Now, if you do these calculations, you will find this unit vector to be minus 0.7 minus 0.71 minus 0.7 roughly 1 and 0. Note that the unit vector doesn't have any units, so I don't need to include m here or anything else. These are unitless numbers. Okay, now that we have everything here, now we have to take all this information and plug it into the expression for the gravitational force. So what I need here is the minus sign, g, the two masses, the magnitude, which I have here squared, times the unit vector r hat, which I have right here. So once you're done with the calculation of the unit vector, just plug in everything to this expression, do the calculations, and you will get the result. So this would be the gravitational force from the star on the planet minus, I'm looking at this expression, minus g, which is 6.7 times 10 to the minus 11. The mass of the star is 4 times 10 to the 30. The mass of the planet is 3 times 10 to the 24. Then you divide this with the magnitude of the vector squared, so it will be 7.1 times 10 to the 11th, and you have to take the square root, the square of all of that, and then this will be times the unit vector, which I have right here, minus 0.71 minus 0.71 and 0. And here my suggestion, when you are to do this calculation, my suggestion is to find what number I can show you here. First, find the number that corresponds to this quantity. Do the calculation and find the single number for this. Once you have that number, then use it and multiply it with the x component, the y component, and the z component separately in order to get your final result. If you do these calculations, you will find that the gravitational force from the star on the planet is equal to 1.1 approximately 0 times 10 to the 21st newtons, and this is our final result. Now I want to go back and see if this is consistent with what we knew for gravitational forces before. So at the beginning I said that I expect the gravitational force from the star on the planet to point towards the star since it's an attractive force. So this vector has a positive x component and a positive y component. Now if we go back and we see the final result of our calculation, we do have a positive x component and a positive y component. So this result is consistent with our intuition for gravitational forces, for the direction of this force. So it's good to do this test just to make sure that you don't detect any inconsistencies which may lead you to find a mistake in your calculations.